this video, I shall look at a form of coding which is basically tree coding, which we can call what I can call a bizarre tree coding, because it gives a very strange result that you can actually code a large number fairly compactly, by adding and taking away less quantity than what is actually we think it does. Here what we have is the objective again is to code a number which is less than b power l dash equal to m as a value. Rather than b, I will take since I'm only using the binary case here, that's what really matters, because for all other bases also the ratio comes out to be the same. So we are trying to code a number 2 power l dash as a value within 2 power l, where l dash is much larger than l. The ratio of l dash to l will be the compression ratio. Now what happens here is, when you just look at the conventional binary representation of a number, the ratios again are powers of 2 here, 1 by 2, 1 by 4, and so on up to 1 by 2 power l. Now if we construct a tree of height l rather than l dash, let's start with the ratio half here. Okay. Now I have a tree of height h here. Each of them has a node here, and so on. Height h will, here I am taking height to be this l, which is significantly less than l dash, and then again a height l here. Height of this tree, number of levels in the tree is l of the code. Now this we would require the value 1 by 2 power l dash, and for this we require the value 2 power l dash minus 1 by 2 power l dash, even though the height is only l rather than l dash. So basically this gives rise to we try to determine a value r such that half minus r plus r square plus r cube plus r power l minus 1 is equal to 1 by 2 power l dash, and then half plus r plus r square plus r cube plus r power l minus 1 is equal to 2 power l dash minus 1 by 2 power l dash. This, in other words, we have to determine r such that half minus r by 1 minus r is equal to 1 by 2 power l dash, and half plus r by 1 minus r is equal to 2 power l dash minus 1 by 2 power l dash. You can clearly see this one, you can approximate it as by 1. You can clearly solve these two equations, and you will find out that the value of r always comes out to be 1 by 3. So in that particular binary tree, if xi is a particular ratio here, so this node will be x2i plus 1, and this will be x2 times I plus 1. So the ratio associated for x times x of 2i plus 1 will be equal to xi x of 2 times I plus 1 will be xi plus 1 by 3 whole power I plus 1. This result is bizarre because even if you take a binary tree of height L dash and you are taking away 1 by 2 power I, which is rather than 1 by 3 power I plus 1 is what, but this actually suggests otherwise, so it may seem that this result is wrong, but actually no, it may not be wrong because when we consider the binary representation of a number, this number actually represents only the value of a node at the last level of the tree. That only that ratio is what is being considered here. But this result, what this result is saying is, if you organize the ratios and take away that, given a value n less than m equal to 2 power L dash, if you take a particular node on the tree such that the ratio associated with that node, say Ri, is the largest ratio for which the value being is less than n, less than equal to, then clearly the number will lie between this ratio on this tree and the next successor ratio on this tree. Now that is not how the numbers are coded as two successive ratios. Now we are trying to code it that way. So it says that if you are trying to code it this way, then the ideal ratio to take away is actually, so 1 by 3 power I is sufficient. Then, so this suggests that in general, if we can generate any sequence of ratios such that m times in ascending order, increasing order, between 0 and 1, such that m times the two successive value ratios of that is reduces to some value m dash which is much less than m, and those, then only the ith term of that sequence needs to be coded, and while it cuts the information down, the size of the code will increase only very slightly. So this is a somewhat a bizarre result. It should be able to code. So this suggests that by taking away less and by adding less, you can actually code more. But here we have to remember that it is ratios only. Again, significant way to improve this would be, if you have a number 0 to 2 power L dash, you can code only L dash alone. There will be two ratios such that 2 power L dash into R now, Ri plus 1 minus 2 power L dash into Ri. This is a new value which will be very small, so only L dash alone, or you can code the base alone. There will be two value between 0 and 2 or 1 plus. So you can use either of these techniques to code a large amount of information as a